Hello, welcome to my hot wash video. So my video is going to be about the catalytic triad, specifically focusing on chymotrypsin's mechanism. So to start, here's a little introduction to chymotrypsin. So chymotrypsin is a serine protease enzyme, and it helps to break down dietary proteins in the small intestine. So specifically, it speeds up digestion by making the rate of peptide bond hydrolysis 1.7 times 10 to 11 times faster than it would have been without the chymotrypsin. So it does this by stabilizing the transition states that form during hydrolysis using its special catalytic triad, which is aspartic acid, histidine, and serine. And then also to note, it's not super specific. It is specific in that it'll work on large nonpolar side chains, but it doesn't just focus on one amino acid. It'll work on a large number of them. Okay, so here's the triad. So it consists of serine here, histidine here, and aspartic acid here, and then a little more on each of those. So there's serine. Serine contains this hydroxyl group, and in chymotrypsin catalysis, this is going to do the covalent catalysis. And of course, we'll go more into this as we talk about the mechanism. Histidine. Histidine is important for the acid and base catalysis in this mechanism, and that's due to this imidazyl ring that it has here. And then finally, there's aspartic acid, and that's here. So it can do acid and base catalysis, but in chymotrypsin, it mostly works just to stabilize histidine by hydrogen bonding to it, so that histidine is able to work more efficiently as an acid and a base. Okay, so step one of the mechanism. So first, histidine is going to do some basic catalysis. So for all these photos here, I drew them just to separate out each stage and make them a little bit more clear, but important to note, when I was drawing these, I didn't make this section of the images super specific to what's happening here, because this is the more important part in my mind. And all you really need to know here is that aspartic acid is hydrogen bonding to this nitrogen here, so I can stabilize it so that this nitrogen is better able to act as an acid and a base. So that's why this part isn't super specific, but this part is kind of where most of the action is going to happen. So anyway, the first step. Histidine is going to act as a base right here. It's going to remove the hydrogen from the serine, allowing it to be a more powerful nucleophile. And it needs to be a more powerful nucleophile because it's going to go ahead and attack that carbonyl group, the carbonyl carbon, off the backbone of the amino acid here to form a covalent bond. And this is the bond that it's going to form. And it's going to form this unstable tetrahedral intermediate. But luckily, we have the oxyanion pocket that's going to stabilize this through hydrogen bonding. Here's that pocket here. So this is where the negative charge would be. And then these nitrogens in the backbone of these amino acids are going to help stabilize it through hydrogen bonding. But still, it's unstable, so it's going to want to collapse. And that brings us to step 3, or histidine acid catalysis. So basically here, the histidine is going to act as an acid, and it's going to donate an H to this nitrogen here as the tetrahedral intermediate collapses and cleaves the peptide bond. So here, it's going to come down, and this is going to be the leaving group essentially. It's going to grab the H, and it's going to break off. And this is a C terminus that's leaving. But we're not quite done yet, because we still have this acyl enzyme intermediate, and so part of this peptide is still connected to the enzyme. So the enzyme is not restored to its original state yet, so we still have more to go. Brings us to step 4, and this is going to look kind of familiar because it's basically a repeat of what happened in steps 1 and 2, where the histidine is going to act as a base, and then the water is going to perform covalent catalysis. And this is because when we formed that initial covalent bond with the serine, we're going to have to take it away, and so that's what this step is all about. So first, water arrives, and I put an exclamation point because usually that's not a good thing, but in this case, it's a good thing. And basically the histidine is going to do the same thing as it did before. It's going to act as a base, it's going to abstract that hydrogen, and then the resulting hydroxide is going to be a better nucleophile, and it's going to be able to attack that carbonyl carbon and form, again, this tetrahedral intermediate. This covalent catalysis is what just happened here. Let's see if I missed anything. No. Okay. And then here's the part where the enzyme is going to regenerate. So again, we're going to have this collapse down, but instead of last time, it was a leaving group grabbing that H, that C terminus, that nitrogen that left, and a cleavage of the peptide bond. Instead, it's going to cleave this catalytic bond between the protein and the enzyme, the substrate and the enzyme. So again, the serine's oxygen is going to grab this H from the histidine. The histidine's acting as an acid, and it's going to separate, and it's going to restore the enzyme to how it originally was. And then the rest of the substrate is going to leave, or the product now. Let's see. So that's basically the mechanism, but there are still some key points to remember. And just like as a summary here, it's going to be the same kind of process repeated twice in this enzyme. There's going to be a base catalysis, a covalent catalysis, first time with a serine, and then an acid catalysis to cleave that peptide bond. The second phase of this cycle is going to be a base catalysis, a covalent catalysis, this time with water, and then an acid catalysis, this time cleaving that initial covalent bond between the enzyme and the substrate. Because if you form covalent bonds, you're going to have to remove them in order to restore the enzyme to its original form, because the enzyme is going to remain unchanged at the end. And then also just to note, there's more going on besides this triad in the enzyme. Like, for one thing, there's the oxyanion hole, and I know we focus on the triad, but there's more to it than that. I just want to note that. Okay, then also, other enzymes that use a similar mechanism, so other serine proteases. So for the sake of time, I'm only going to talk about one in the video, but I'll leave the link to the Prezi, and you'll be able to come and look at the other ones if you'd like. And the one I want to talk about, because I think it's the most interesting, is subtilicin. And I think this one's the most interesting because it evolved completely separately from chymotrypsin. Like, completely separately. If chymotrypsin evolved in humans and maybe animals, subticillin evolved in bacteria and plants. And yet, it still managed to evolve that exact same triad of serine, histidine, and aspartic acid, which I think is pretty incredible. And so it does the same thing. It cleaves peptide bonds. And so we're able to use it mostly as laundry detergent because it can break down that food and that grass and that blood that ends up on our clothes. And here's what it looks like. And I just think that's interesting. Then the other ones are thrombin, and you can also look at trypsin. Let's see. Alright, here's my sources. And that was the catalytic triad through the mechanism of chymotrypsin. Thank you.